stress in any of the directions other than the x direction. So the only non-zero component is the x stress.
Is that correct? Yeah. Okay, that's perfectly correct answer. Right? So now, I didn't have to tell you straight, you already knew this stuff, right? But in terms of a three-dimensional problem, this is, so the normal, the uniaxial tension or compression, the compression will give you, so compression is a negative stress. If you think about the cube, outward is the positive, inward is negative. So look at my notes, the PowerPoint slide. One of the slide has the notation for the positive and negative. When to call what's tension is positive stress on the cube, compression negative. For shear stress also is a definition. Positive direction, the positive phase. Positive phase means that the normal is in the positive direction. In the positive is positive shear stress. In the phase that has the negative normal, the negative direction stress. This shear stress is the same as this. Both are positive. Look at the notation. But following that notation, if compression was here, it would have been minus sigma. But this is how you present it. So now, why is it powerful? This is a very common. You characterize materials using simple tension test. You can simplify the bone and the forces using simple tension test. But guess what? When the bone is under compression, is twisting, torsion, we haven't learned how to combine those two together. They're not. You learn that as a scalar. You learn the scalar. This is sigma xx, so sigma is easy in the cylindrical coordinates. Another one was sigma tau theta z or sigma theta z. Right? You can't just sum them up. In a three-dimensional thing, they are acting in a different plane, different directions, right? So how do you add it up? If you're able to write for the same basis, simplified solution, then you can sum up the matrix as long as the basis is same. Now you can combine a lot of complicated problems, and I'll give you enough homework problems for you to do this. So pure shear. If you have shear going like this, so what Jacob said before, you pick a coordinate system. Again, if I make it some arbitrary angle, my life will be very difficult. But if I wisely choose, I can write. I know from my basic knowledge what stresses are there, right? So for this one, if I choose x and y like this, and z goes out like this, then your stress matrix representation for this coordinate basis. Again, like I said, once you pick the coordinate basis, you're working in the matrix format. Everything is for the class purpose in the matrix way, right? So if you look at the cube is oriented along the side, there's no normal stresses in this case, right? If you look at the symbol of, again, imagine the cube here, what direction it is. So this will be
Will there be symmetrical shear?
You with this coordinate system, this is what these. So these are the components I filled here. You're absolutely correct. Is that what you're asking for here? Mm-hmm. Yeah. So if you see a stress tensor that's not symmetric, strong, right? I didn't pay attention, so thank you. That will be so. Again, pure shear. The torsion was pure shear. So imagine torsion case. If you can write you can pick the cylindrical coordinate system r theta z, and the only thing is tau theta z, which is sigma theta z, is non-zero, is that one. So everything else is zero except those sigma theta z and sigma z. Okay. For this coordinate system, you can always write these things down. Like I said, this is not only the biomechanics, solid mechanics, fluid mechanics. Everything is fluid, solid. The same ideas apply. In fluid, you have heard the concept of hydrostatic pressure. So imagine the cube. Pressure is acting normal to it. So all the surfaces, only normal stress is acting. There's no shear stress is acting. So imagine the cube. Then, and if you align x, y, z. So all the shear should be 0 for the hydrostatic pressure, right? Because only normal stress is acting. What goes in the diagonal component? Or
whatever the pressure.
what sign should I use? So let's imagine, what is pressure? Pressure works inwards, right? Okay, so remember how we define sigma xx? So that's all we need to add. In biomechanics, this happens a lot because a lot of tissues are thin membranes, we have in the planar dimension stretching. So equibiaxial means that you have in the third direction the stresses are 0. Is that the alarm for me to stop teaching? Okay, let me give it 10 more seconds. So, I mean, you look at my notes, I have the coordinate system drawn. Basically, you choose the most wise coordinate system that you can. This is same as following. The reason I gave you some of the simple cases which you can solve otherwise, they all fit under the 3 dimensions. So now you can do, if you have used the same basis, you can superimpose stresses. You can sum up stresses. So simple cases, if you know, you can write down the stresses for torsion, bending, uniaxial pressure, internal thing. And as the coordinate basis is the same, you can sum them up to actually solve for a very complicated problem. Alright, I think the alarm went off, so I'll stop here. And I think this much pretty much covers the stress, but we'll talk about the other step. Who brought it up? So I said, if you have stress tensor, there's one unique configuration which is eigenvalue, eigenvector. This is 0 shear stresses. But somebody said, you know what? I don't care. I'm going to pick an arbitrary coordinate system. Tell me what stress matrix will look like for that. So I want to give you a solution for that as well. So you can solve for any arbitrary. And when you solve failure problems, it will all make sense why we do this. Until then.
But then I only want to make two.
Yeah, I'm a good guy. Just make sure you tell me like 0, 9, keeping up.
I don't know.
It's so annoying. I can't wait. It's okay. I'll do it.
Okay. Yeah. Okay. Also, so you said that. Yeah. If that doesn't work, I just realized that it's actually optional to have it. So if it does not work, do not worry at all. I will. Just there. I just realized. Oh, wait. So they do have one. You can bring your own. Or you can
go upstairs. Really quickly, for your first one, on your notes, you said,
But then if they're gonna give you one.
Yeah. And so I just realized this today. I'm so sorry. I did not realize this earlier. So I'm sorry for all the confusion.
No, yeah. I'm glad you
0.
worked out.
Yeah.
I thought I fixed it.
Alright, good
Oh,
to know.
okay.
Okay, great.
It's symmetric always. If it's not symmetric, it's wrong. Did I can't fix that. Yes, that's there.
I'll see you.
Yeah. Just like that methodology is fine.
Yeah.
Only one pair. Yeah.
Do I have to do that?
No.
Yeah. I have a HDMI cable.
Oh, yeah, you went right from home to University College, right?
Yeah, exactly. Yeah.
Do you have any audio on your presentation?
No, I don't know. No.
So that's the screenshot. So
Okay.
you should be able to walk to either side of the screen.
Okay, perfect. Okay. I'll try and slide. I guess we'll be here. Yeah. Cool. Thanks. You're really leaning into the noon and fall kind of vibes.
You can use the stick if you want. But
Yeah, instead of a hockey stick, have a nice.
yeah, but sometimes I think speakers commit to the stick and then get kind of tired of holding it. And you can see that technique is there. So, you know, if you choose it, then just beware that you have to hold it for the whole time.
So upper arm strength test.
source paper by Gankow's group of Boulder. The title of the paper was like the most, I think, keywords I've seen in paper title was like a trimer-based cluster modulator. So the title had like trimer, cluster modulator, spin liquid, strange metal, all in like one
All in
title.
one, yeah.
Yeah.
I remember there was this. Yeah, there's this trimer system that they're working on called the spin liquid.
Yes, but it's also strange metal somehow. I was looking for
Yeah.
There's a lot of fancy words in London.
Yeah. Disordered or something.
yeah, unfortunately. I see that.
Oh, no. Who's not?
Okay. So we're lucky to have Ciarán Hickey visiting us all the way from University College Dublin. Ciarán got his PhD working with Arun Paramakanti at University of Toronto. He was working on, mostly like strongly spin orbit coupled frustrated systems, but it seems like actually a pretty broad array of things, and made some nice contributions there. And then moved to Cologne for a postdoc working with Simon Trepst, continuing to make more interesting contributions to frustrated magnetism, some connections to some pretty exciting experiments with like the trichloride at the time and other things. And then after that, moved on to start his own group at his undergraduate alma mater, University College Dublin, where I guess you've been working on some frustrated magnets, other interesting cluster magnetic systems, and then also hopefully maybe telling us how to do more informative measurements on quantum spin liquids than we've been able to do in the past. So I'm excited to hear about that, and thanks for visiting us here.
Yeah, no, thank you, Ken, for hosting me. It's my first time in Rhode Island, or Graham, so it's been a very nice day so far. I'm enjoying all the New England decor all over the place. And so I'm going to tell you about nonlinear spectroscopy, which you might have heard about because in the area of optics, if you open up a nonlinear optics textbook, nonlinear spectroscopy or multidimensional spectroscopy is the backbone of the field of nonlinear optics. But in recent years, it's been kind of ported over to quantum magnets and superconductors, too, which I won't talk about in this talk. And so it's kind of actually quite a different perspective, because rather than using, say, multidimensional spectroscopy for looking at small systems like molecules or proteins, and we're really thinking about many body systems, systems with collective excitations, order parameters, topology potentially. So it's really bringing this kind of technique into a different arena. So there's been a lot of ideas into what you might see with it, some experiments also. And I'm just going to give a little bit of a taste today, and kind of an extended introduction, because it's something that you might not be super familiar with. But this work is not done in isolation. And so it was a couple of different works, and also my current group, it's in Dublin is also working on the same topic, at least some of the students. And I just want to highlight about everyone here. I'm Yoshida Watanabe, who's a brilliant postdoc at Cologne, and he's done really a lot of the, as you can see, a lot of the work that I'll be talking about today, and he's really an expert. Okay, so before kind of getting into the nonlinear spectroscopy itself, just want to give a little bit of framing or background. Let's say that you have some quantum many-body system. It could be a magnet. It could maybe even be an artificial system like atoms or maybe something else. And you'd like to study it, okay? And like I said in this talk, I'm going to mainly think about magnets. So I'm going to think about, I have a magnet in the back of my head. And you want to learn more about it. So there's two perspectives you could take. You could look at static properties of the system. Okay, so how things are correlated in space. So for example, for a magnet, you might look at in spin, how the spins are correlated in space. Typically, we don't look at these correlations in real space, but in momentum space. Right? So we might look at, say, the static structure factor, the Fourier transform of this, and Bragg peaks. So sharp peaks in this will tell us about the magnetic structure. Or you might have a more complex kind of structure. So this doesn't have sharp Bragg peaks. This is a theoretical calculation for a more exotic kind of ground state structure. Okay, so on the one hand, you might look at these static properties or static correlations. On the other hand, though, you might look at dynamics, okay? And in this talk, I'll only talk about equilibrium dynamics. So everything's in equilibrium for the rest of this talk. There's no non-equilibrium dynamics. And so you might look at things like this, how excitation values velocity between times. Okay? Again, for spins, you might look at the spins, how spins fluctuate, not just in space, but also how they fluctuate in time. And again, we usually don't look at it actually in real space or time, but we Fourier transform it. And so we look at someone say like the dynamical structure factor, as a function of momentum and energy. What are the dynamics of what are the excitations of in this case, magnet? Here's a square as n for magnet and some sharp magnet modes. Right, and obviously these are not disconnected perspectives. There's an intermittent relationship between the static properties of a system and its dynamic properties. And these kinds of correlations, both of them can be put into the same umbrella, all kind of linear response. Okay. So what I mean by that, we have our system, it's described by some Hamiltonian, and we perturb it in some way. So for a magnet, I'm going to apply some magnetic field. The magnetic field could in principle have some spatial and time dependence. And if I think of this as a perturbation, so I guess I'm not like, violently shaking the system, but I'm really just gently poking the system, okay? If I think of like a perturbation, I can expand the induced response, so the induced magnetization in this case, in powers of the perturbation. And so the, first term I'll get here is something that's linear in the magnetic field, so the applied perturbation. And here, this function here, chi, this linear susceptibility, tells us about how the system responds to this perturbation. And there's expressions, you can look up your undergrad textbook. The expression for this is exactly in terms of these correlations in space and time that I had in the previous slide, okay? And so by perturbing the system, gently poking the system, looking at how the system responds in space and time, and we can extract information about the correlations of the spins across space and time. Okay, and so let's do a super simple, easy example of this. I'm doing this now just because I'll complicate it a little in a second, okay? But let's say we take a super simple magnetic field, which is a uniform magnetic field, so it's uniform in space, and it's just a delta function of time, okay? So it's like a sharp pulse. Okay? And it's a uniform field for the rest of this talk, basically. So I'll only talk about basically Q to zero physics. So if you're doing kind of neutron scattering and you're interested in looking at, across all momentum space, unfortunately here I'll need to be restricting myself to Q to zero physics. So everything couples to the total magnetization M. And so then I expand the induced magnetization, in terms of the magnetic field. It's chi1. This has an expression, like I said, in terms of correlations of this magnetization. This is exactly, so this correlation function is exactly what you would measure inside the dynamical spin structure factor Q equals 0. Okay, so if you look at the Q equals 0 part of the dynamical spin structure factor, you're looking exactly at the same kinds of correlations of the spins. And these are related by fluctuation dissipation. Okay, so let's take a super simple example. You take the ferromagnetic phase of the 2D transit model, so all the spins are pointing up. You look at, say, the XX, chi XX. This is what it looks like in time. Again, we look at the frequency. This is the Fourier transform. I see there's a super sharp peak here at 2. I set j equal 1 here in this model. And this peak here is just the excitation of the spins are pointing up, and you just flip it down. Okay. You might be able to see there's a teeny tiny peak here at 3. So 3 is because if you flip two excitations that are right beside each other, That's actually a slightly lower energy than flipping two excitations separately. So that's 3. And then it's basically not possible to see, but there's an inequality of 10 p. Okay, so this is a super simple example of what linear response might look like for a super simple magnet. Okay, so this kind of framework, thinking about perturbing the system, looking at the response, see how the correlations behave. They try to be powerful, and it underlies a lot of the kind of probes that we use in quantum physics. Okay, so a lot of the things, kind of experiments or techniques we use, can be put into this kind of framework. Okay, but it doesn't necessarily give us every single piece of information we might want to know about a system. Okay, there's no guarantee that just because we do this kind of linear response thing that we're going to get all of the information. And so sometimes it might fail to capture key physics. And so if that happens, the question is, what do you do instead? Okay, what else can we do? And there are 2 examples where it might fail to capture key physics, which I'll touch on in this talk. One is the case in which the linear response is rather broad and featureless. For a magnet, this might be kind of famous cases where you have a broad featureless continuum. Another example might be kind of excitations that are not visible or barely visible in linear response that have almost like little to zero weight. Okay, so what can you do instead? Well, beforehand, I threw away. I couldn't say it. I threw actually away a bunch of stuff. Right? So there's a ... here when we're looking at the response. So there's a lot of information here we've thrown away. So these are the so-called nonlinear susceptibilities. Okay, so these higher order terms here. Right, so we're on this side here. For this talk, we're talking about dynamics and equilibrium. But rather than looking at these kinds of correlations and the nonlinear response, we're actually looking at higher order dynamical correlation functions. So there's multiple operators and multiple times involved here. Okay. And so nonlinear response is talking about these kinds of correlations as opposed to the kind of correlations that we looked at here for linear response, which you might see say in the dynamical structure factor for magnet. Okay, so then there's 2 perspectives you can think about for nonlinear response. You can think about you're perturbing the system, you're gently poking it. You're looking at the response, the physical response of the system, so it's the induced magnetization in this case. And you're looking at the part of the response that's higher order in the probe or in the perturbation side, so squared or cubic. Okay. This is physically what you're doing. Or if you're a theorist, like myself, you might also just think about it. We're looking at higher order dynamical correlation functions. So we're looking at these kind of more complex correlations of the system. Yeah, these are equivalents. All right, so then there's 2 very obvious questions you might have. One is why. So what's the point of doing this? So what new information can we actually learn? Right? In some sense, these more complicated correlation functions have more information. But just because they have more information doesn't mean it's useful information. It might just be more, maybe it may not necessarily tell us more than what we get from the response, right? It might be redundant. The other thing is that there may be more information there, but maybe extremely difficult to extract, right? So maybe these are higher order correlation functions. There's more arguments. They have a much more complex space they live in. So maybe that actually extracting this kind of information is extremely difficult. So what new information can we learn, if any? And of course, the other super obvious question is that we're doing physics, right? The other thing is how. So even if you can get some interesting new information, at the end of the day, you have to physically measure this, right? So how do you actually physically measure it? And this is a much easier question to answer because this is just borrowing, the techniques from nonlinear optics and just putting it onto a magnet. So we're going to describe this first. It's just a simple, very simple modification of the previous example I did. The previous example I did a single pulse. I'm just going to put 2 pulses in, okay? And there's a time delay tau between these 2 pulses, and a second time delay t between the second pulse and when you actually measure the magnetization. Okay, so the magnetic field I can write now is 2 delta functions. Okay, you get a uniform magnetic field. And so then I can expand the induced magnetization like this. Okay, so I get these linear terms. I've also now written down these chi2 terms, so these are the second order terms. And then you experiment twice more again, okay? So you do it once more with just the first pulse, and then a second time again with just the second pulse, okay? And now you can subtract these single pulse responses from the 2 pulse response. And you can see here that if I do the subtraction, this part here will cancel with this part here. This part here will cancel with this part here. This chi2 I will actually cancel with this chi2. And we're going to be left with these mixed terms. Okay, so this mixed response. Okay, so by doing the subtraction, you eliminate the linear response, which is the part that will dominate your signal, right? If you do this experiment, you will see a huge linear response. That's why linear response is so useful. And so if you want to see this high order stuff, in some cases, it may be that this is so strong that you can actually see it already kind of on top of the large linear response background. But typically, that's very difficult. And so what you want to just subtract away this large linear response background so you just get, as the lowest order parts, the nonlinear response. Okay, so the Chi2, or in some cases, this may manage.
Can I just ask a quick
sorry.
question? So when you talk about the first and second pulse,
Yeah.
what sets your clock? Or do you just wait twice this time to set some, like, how do you know you said you do it with just one pulse, first pulse,
Yes.
and then you do it with the second pulse? Are they different? The only thing that varies between them is length, or something has to set the clock?
Yeah, so
Or is
basically,
it the
so
phase?
basically the time, so really, you're right. The time before a pulse is basically the same in both cases. So the only thing that will be different is the way in which you're treating the time arguments. So, this thing will be a function of t and tau. And so the two time arguments. And so this one will be, there'll be some like equilibrium dynamics here. You'll hit this first pulse. Then there'll be the induced dynamics. And for the other one, there'll be some equilibrium dynamics that will
So
be
you just
all the way
wait
here.
longer before this.
Yeah, exactly. And then exactly, yeah. And so there'll just be equilibrium dynamics here because of the pulse, and then you hit the pulse, and then again, exactly.
So practically speaking, in real experiments, do you actually have to do multiple experiments and subtract the background, or can you do it in a single shot?
Yeah, I will come to the experiments in a second. So for the experiments, you basically, I'll come to that in a second. Okay. If I haven't answered, I'll come to it, and if I haven't answered your question, then let me know. Okay, so this is the cartoon still. So, oops, sorry. Okay.
But so both pulses have to hit the system when it's in equilibrium. So then tau has to be longer than some relaxation time in the system, or?
I guess you should think about these pulses as really weak pulses.
Okay.
Yeah. So the first pulse excites the system. It may not necessarily relax all the way back to equilibrium by the time the second pulse hits, right? Because you don't want it to in some sense, right? Because you want the second pulse to act on top of the first pulse.
Yeah.
Because if it relaxes all the way back to equilibrium, then it's just like doing two independent.
That's right. Yeah, that's what's right.
Yeah.
Okay.
It's in equilibrium, and the whole thing's equilibrium in the sense that it can be described in terms of the equilibrium properties of the original system.
Yes.
So you're not driving it into a non-equilibrium state, but you're really probing the equilibrium correlation of the original system. Okay, and then these Chi2s and 3s, they also have expressions. You can look them up in an optics textbook. Used to replace all the electric fields in the optic textbooks with magnetic fields and all the polarizations with magnetizations. And so they have some more complicated looking expressions, but basically this Chi2, so the second order thing, has 3 magnetization operators in it. And Chi3 has 4 magnetization operators, and they have multiple time arguments. And there's different ways in which you can order these time arguments. That's why there's multiple. The ... here are just different ways of ordering the time arguments together. Okay. So this thing is not new. Like I said, it has a name. So it's two-dimensional coherent spectroscopy is a typical name. Two-dimensional because I'm using 2 different times here. So in multi-dimensional spectroscopy, you can have multiple pulses. Okay, so more than 2 pulses. And it's been used for many, decades. So in like chemistry, for example, it's very popular. Here's a nice example where they look at there's certain molecules that are bonding. So there's the hydrogen bond here. And at some point in time, this bond breaks. And basically, by looking at these particular peaks here, the disappearance of these peaks indicates that this bond breaks. And so by kind of measuring this as a function of time, you can get access to the bond breaking.
And Barry, with one more technical issue, what is coherent here?
Yeah, that's a good question. I think I don't have a good answer for you because I haven't come up with the same.
Okay.
I think it's the laser sources. I think, but I wouldn't
That's
have.
Nothing else. It's not like the poly. Yeah.
No, I don't think
You
so.
don't do the
I don't think there's any deep.
It's just drive. Yeah. So laser. Yeah, it has to be a laser pulse.
Yeah.
Just another, maybe this is a silly question, but when you showed the correlator expression, the Chi2 was the real part and the 3s were the imaginary part.
Yes.
Is there any important, is there in the linear response that we think of it like the real part is the dissipative part, the real part is the reactive part and the imaginary part is the dissipative.
Yeah, I think that's the. If I go back for a second, here in time, it's also the imaginary part. It's really just this, and then the conjugate of this, which you can put as the imaginary part. And then once you Fourier transform this, because we're typically looking at frequency, the Fourier transform will be complex.
Yeah.
And the real imaginary parts of the Fourier transform we would call like observer.
Okay.
It might be easier to think of it in terms of derivatives. This is like the first derivative term in time. That's what makes it the imaginary part in the frequency domain.
Oh, okay.
And then you switch, and then you go to successfully higher derivatives.
Yeah. That makes okay.
Yeah.
And that also makes your amplitude go down, right?
Oh, yeah.
Every successive term is the square of,
Yeah, yeah.
in terms of signal to noise, right? If you try to.
Assuming you're in the quasi-equilibrium regime, which we are.
You always get
Yeah,
something.
yeah.
Yeah, so everything will be suppressed exactly as you okay. Yeah, and so it's also been used in, like, say, semiconductors, TMD looking at excitons. It's quite popular. And then there's many other applications. Also going all the way back to the 70s, like 2D NMR spectroscopy in the 70s. So there's a long history of using 2D or multi-dimensional spectroscopy to look at materials. And so what's new? I mean, why did I say at the beginning of the talk this is new? So the new is, in the last 10 years, it's become possible to push this into terahertz. So rather than doing optical nonlinear spectroscopy, this is terahertz nonlinear spectroscopy. Okay, so terahertz is in the kind of picosecond or MeV range. And so this is perfect for looking at magnets, for example, because magnets exactly have excitations that are in the MeV range. Okay, so terahertz is very well matched to looking at magnetic excitations. And here's a trace. This is actually the electric field trace of actual pulses used in one of the experiments I'll show in a second. These are terahertz pulses. You can see the width of these pulses is a couple of picoseconds, so this is quite sharp in time. The peak magnitude in terms of magnetic field, so how strong this magnetic field pulse, is about 0.1 to 0.2 Tesla. Okay, so that's the peak magnitude of these pulses. And the bandwidth, so in frequency, the bandwidth is a couple of terahertz. So it covers maybe up to 10 MeV. Okay, this is again the typical energy range of a lot of magnetic excitations. And this peak magnitude, there's some more recent experiments, but they've actually been able to push this up by a factor of almost 10. And so you can get more like Tesla fields, pulse fields. Okay, and the first experiments were done in 2017, so not that long ago, in the Keith Nelson's group at MIT. I was very fortunate that I got to visit his group last week. I took a photo. This is their schematic. This is the photo I took last week in the lab. And there's a lot of optics here. There's terahertz pulses that come in this way. There's no sample in this photo, but the sample would be here. It's the sample. And then there's a bunch of optics over here for measuring the actual induced terahertz radiation. And so if you do this, complicated thing, you can get the nonlinear magnetization. So this subtracted magnetization I mentioned earlier as a function of these two times, this t and this tau. And again, we would typically not look at it in the time domain, but we would Fourier transform it. So this is what it looks like in frequency. The right is a theoretical calculation, the left is in the actual experimental data. I see that you get a bunch of different peaks, discrete peaks. But they have given names, and these names are kind of borrowed from the optics literature. So the one you might be most familiar with here is SHG, second harmonic generation. Okay, so that's over here. Okay, and this is for a relatively simple kind of canted antiferromagnet. So two sublets kind of canted antiferromagnet with a very, very high moment. So it's iron, so it's been a half moment, and a very high ordering temperature. The ordering temperature of the magnet is the room temperature. So they're like a very well classical magnet in that sense. And in this group, so Keith Nelson's group has done a lot of follow-up experiments, so related experiments, but they've looked at things like temperature dependence, also changing the polarization of the pulses, and temperature dependence, and then looking kind of analogs of kind of nonlinear optics phenomena, like here they look at like magnon three-wave mixing or things like that. Magnon analogs of photon processes, also magnon up conversion, magnon down conversion, and other things. Okay, so this is all for magnets. I just wanted to mention that this has also become, since this has become feasible in the past 10 years or so, there's also people interested in not just looking at magnets, but also looking at superconductors, because superconducting gaps are again also often in this kind of 10 MeV-ish range of excitations. So there are people interested in looking at superconductors. So this is this one is, I think, from Andrea Cavalleri's group. And Peter Armitage's group is also, I think this is from Peter Armitage's group, looking at cuprates, so looking at Josephson plasmons and cuprates. There's also been a lot of work from Eugene Denner's group at EDH, looking at their theory modeling of these kind of plasmons. And then there's also, this is not a superconductor, it's an electronic system. So Peter Armitage's group also looking at this kind of silicon doped kind of glass systems, so electronic stuff. Sorry.
So, do these systems for this 2D stuff, does it need to not be a metal essentially? Because if superconducting gap, if it's a marginal Fermi glass, it's probably some insulating state. Like how? Yeah.
I mean, I guess at least doing for terahertz at 2DCS, you're looking at MeV kind of energies. So typically in an electronic system, the band structure scale is more like EV, so it'd be more doing nonlinear optics as opposed to terahertz.
Right, but like if I want to look at like plasmon or plasmon polariton type physics, right? Would this work for that, or would you like, or?
Yeah, I mean, so I mean, these experiments with qubits in this theory is for Josephson-like plasmons in the superconductors actually. Yeah, so yeah, probing exactly those kinds of I mean, does that answer?
Yeah, that's.
Also, sorry, did I answer your question about how the experiment works?
I was wondering if you could do it single shot without subtraction.
Oh, sorry, yeah. Sorry, but that's a subtraction. So you can do it single shot in the sense that you can. So the way that these experiments were originally done is that you would fix tau, this time delay, and then you would also fix t, and then you do a measurement, and you would change t and tau, and do another second measurement. So it's quite expensive. Yeah. Now they do a single shot technique, which I think is different to the single shot you're thinking of. Okay. Which is that they measure all t at the same time. So they fix tau, the interpulse delay, and they're able to measure all t at once. I see. And then they have to shift tau. So they only have to shift tau basically. I see. So for each tau, they can basically in this there's like a optical element here, which basically beforehand they use an optical probe pulse to basically the nonlinear magnetism that's induced. There's an optical probe pulse that basically measures what is the electric field here. And then for each tau, you basically have to step along and measure it. And now they have basically a crystal kind of grading here that this optical probe pulse gets split out into like multiple pulses that are separated out. And so then each one of those can basically, because they're separated out in time, they can measure this entire thing all at once. So their single shot technique is measuring all t at once. I think the single shot you're thinking of is doing all of the subtraction at the same time. I think they cannot do it. I think.
So in other contexts in condensed matter, when you do this kind of spectroscopy, you actually you play with the wave vectors of the light, and in fact the nonlinear signal occurs at a particular wave vector primarily, and that does the equivalent of your subtraction for you.
Right. Yeah. So here, I mean, for example, if you're familiar with these like double-sided Feynman diagrams that they use for like optics, they're obviously Q is paid by the incoming and outgoing wave vectors, so all the K's. Here, basically, because we're using terahertz, I mean, it's basically a uniform field of the sample, and so we don't really, in these double-sided Feynman diagrams, basically the wave vectors don't play a role. And so, but you're right. I mean, in typical nonlinear optics, it's not just the frequencies, but also the wave vectors that are taking control of that. And so here I basically won't, I also won't draw double-sided Feynman diagrams. But if I did draw those Feynman diagrams, I wouldn't basically include the K's. Wave vector. So wave vector matching and things like that are not.
Another quick question on this: since you drew the sample as thin, does this only work for relatively thin samples that have transmission in terahertz, some kind of transmission through in terahertz?
I mean, so so I mean, I don't. This is I think I'm a meter scale. So obviously, you need the samples. I mean, if it's so you're measuring the you're measuring the your terahertz pulse hits the sample and induces some magnetization dynamics. That magnetization dynamics produces terahertz radiation, and you're measuring that.
But it's only transmission. It's not like reflectance.
In this particular setup, you're measuring the transmission.
You do really need like a cuprate material or whatever. It needs to be a magnet needs to be a thin film.
I wouldn't say film. I mean, a crystal is fine. I mean,
Oh, okay.
I mean, maybe not an enormous crystal, but
sure.
A regular crystal is fine. So it doesn't have to be a special thin film, right?
But does it have to be thinner than a wavelength of the terahertz, right? So not to get the.
So terahertz is about so.
Yeah, huge.
So you wouldn't be using enormous samples, but I mean, I'd say for a lot of.
The area actually has to be pretty big because of the terahertz.
Right? So that's probably samples, that's true. So I mean, the materials they've looked at so far are quite straightforward, like easy to grow materials, so YFO, EFO. I mean, there's no issue with. I mean, the crystals that have a huge. Yeah, then I also just want to mention, although we'll talk about spectroscopy exclusively in this talk, nonlinear response in general has become quite popular. It's quite a buzzword these days in electronic systems. So for example, what is, I guess, also kind of spectroscopy, but looking at, say, probe of symmetry breaking. So this is a famous one from David Shee's group, where they look at second harmonic generation as a probe of inversion symmetry breaking that recuperates here. Or recently things like nonlinear Hall coefficients have been used to probe band structure topology, so more complex structures of the band structure. And there's a lot of dot again. Okay, so there's a lot of people interested in looking at nonlinear response, in transport or in other areas and beyond, or in noise, for example. So beyond spectroscopy that I'll talk about right here. Okay, but I'm going to stick with spectroscopy. And I want to, go to this question of what can you learn, of what does it look like, okay? So let me start by, first maybe cautioning that the interpretation for the nonlinear spectroscopy is a little bit more challenging compared to linear spectroscopy. So you might think, okay, it's 2D spectroscopy, I have another frequency axis, okay, now my plot is 2 frequency axes instead of 1, okay, straightforward. Actually, it's conceptually a little bit more challenging, especially for theorists. So if we look at the linear response, you can write the chi1s, the linear response, like in this kind of representation, where it looks like a delta function, which just gives you energy conservation, at times with matrix elements. So here you go from, say, the ground state to an excited state via the magnetization operator, and you go from that excited state back to the ground state, okay? And then, with an energy of that excited state. So this is what, say, if you're familiar with the dynamic structure factor or Layman representations, this is what it looks like. So matrix element times a delta function. So then if I sketch the linear response, it might look like something like this. And there's a very clear meaning to, for example, kind of low energy and high energy, in the sense that the signal is ordered in the same way that the energy spectrum itself is ordered. Right? So the energy spectrum goes from the ground state all the way up to high energy, and the signal is also goes from the ground state all the way up to high energy. Right? So the ordering is exactly identical. This is a super trivial statement. I'm just going to contrast in a second. The other super trivial statement is that these finite matrix elements give you a finite signal. In this case, I put the same index, so this is actually just n0p squared, mod squared, so it's a positive number. So every finite matrix element gives you a finite signal, okay? So you start here, over here, you go along, to increasing energies, and every time you have a matrix element, you get a little peak, or a little feature, with an intensity that's proportional to the matrix element. So super trivial, okay? So what about the nonlinear susceptibilities? So here's an expression for one of the chi3s. It has more matrix elements, okay, because it has more operators in it. And it has a more complex structure of energy conservation. And so you might think that I could do something similar like this. That was like low energy is kind of close to the origin or close to the axis, and high energy is kind of away from that. It's actually not so straightforward, because what I notice here is not just energies, but also energy differences. So it's possible, for example, to have two high energy features that are very high in energy, but the energy difference between those features is small. And so then they don't enter necessarily with a high frequency, but they may enter with a small frequency, okay? So they can enter close to one of the axes. And so then you can have, here the low energy features are separated from the high energy features. So if you have a theoretical tool or technique that treats well low energy physics and maybe doesn't treat so well high energy physics, which is a lot of the techniques we use, and it's fine here because you know that, okay, you can qualitatively describe this low energy region. Here you can have low energy features right beside high energy features. Okay, if the high energy features come from two high energy things that are close together in energy. And so this is kind of mixing between high and low energies. And so for modeling purposes, this is difficult then, because you then need theoretical tools that can treat not just well the low energy physics, but also capture high energy physics too. And the other thing that's, so this is contrasting this point. The other thing that's complicated here is that these elements are not strictly positive, not strictly positive, so you can have cancellations between matrix elements. And actually cancellations can be important. And so it's not just, oh, this matrix element is zero, non-zero, I get a peak or not a peak. You can have all sorts of cancellations occurring because you can have different processes canceling out. And this actually is quite subtle and can lead to real headaches for, us theorists when we're trying to calculate things. Now you can have two types of cancellations. The cancellations occurring that shouldn't be occurring. So for example, like naive application of the spin wave theory to this, on your responses will give you missing peaks because of cancellations that occur that shouldn't actually occur. Then you get cancellations that should be occurring that don't occur. So for example, if you restrict the number of excitations, so you truncate the space that you're looking at, you can get cancellations that don't occur, so you can get kind of things like extensive signals. So there's actually a lot of issues with kind of controlling these cancellations when you're doing theoretical calculations, which can be a real headache. And the last thing is a kind of technical thing to do with the experiments, which is to do with the fact that all the way in the back when I gave you these expressions for these chi2s and 3s, they had these heaviside theta functions as a function of time, which basically enforces causality, obviously. And if you have actually, and the same thing is true for linear response, we also have a heaviside theta there for linear response. But once you do the Fourier transform for these two theta functions together, you actually get what's called phase twisting, which is a kind of artificial broadening due to this kind of particular constraint that doesn't occur in the linear response, where it can be separated into these real and imaginary parts. So there's an additional kind of artificial broadening that's just due to the special structure of the Fourier transforms. That's physical in the sense that it comes from a physical origin. I mean, this causes a lot of constraint. But for interpretation purposes, it can be annoying because it can maybe not be clear whether the broadening you're seeing is just this artificial broadening or broadening due to a real physical process. So that's a kind of, for theorists, we don't have to worry about this too much because we can remove this. But for experimentalists, this is more good. And again, it's discussed heavily in optics, how to deal with this. Okay, so let's do a simple example. So the simple example is just a two-level system, right? So spin up and spin down, split into omega naught. If you look at the linear response, you'll just see a single peak at 2 omega naught, right? The excitation frequency. This is the chi x xx. If we look at say chi 3, and I've chosen one of them, I'm going to get something like this. So there's 2 peaks, and now I'm drawing a 2-dimensional frequency space, right? So how do you understand these 2 peaks? You can understand this kind of process where it's a little small. You start at the beginning of the ground state, which is spin down. At time 0, the first pulse acts an M operator. So you go from up to down, so you're in the excited state. So you evolve with a frequency that's plus or minus 2 omega naught. Then the second pulse acts, and it acts twice. So you go from the excited state up to the ground state down, and back to the excited state again up. So you time evolve omega t with plus or minus 2 omega naught. And at the end, this final pulse, the measurement kind of acts. And you go from the excited state back to the ground state again. So during this process, you either pick up the same phase, so plus and plus, or you pick up opposite phases, plus and minus. Okay, so this plus and minus case there with phasing is very much like kind of like an echo, right? So you pulse the system and you evolve with frequency omega, and you pulse again, you evolve with frequency minus omega. Anyway, so obviously, if you do that, if t and tau are the same there, then you get this kind of echo enhancement. And again, these names are taken from optics. This is not a phasing or phasing peaks. Okay, let's make it slightly more complicated. Instead of a single 2-level system, let me take a collection of 2-level systems with frequencies, a continuous range of frequencies. Okay, so it's the exact same. Here I had a single 2-level system. Now I'm just taking a range. I'm just taking a continuous range of frequencies. So the linear response, beforehand I had just a single delta function. Now I'll have a bunch of them, but I have a continuous bunch of them that just looks like a big broad. And over here I had just single dots, and then they get extended into lines. Okay. And for this phase twisting kind of reason I mentioned, it's a bit technical, this line actually disappears, or it's not visible. So it looks like this. Okay, so why have I chosen this? It's a simple extension of what we just did. We've actually already solved our first many-body problem, because you can write the 1D transfer Ising model in exactly this language. There's a transformation between these t's and these taus. And so this is actually the linear and nonlinear response for the 1D transfer Ising model. So there, the interpretation of this broad continuum, or these 2-level systems, is that when you flip a spin in the transfer Ising model, the fermionic phase, you create domain walls. Okay, so you have the ground states all spin up, you just spin down. You create these domain walls, and they can propagate as free particles that have a momentum k minus k. And so then, because you have momentum k minus k, you basically get a continuum of these excitations. And this is kind of like a baby version of the kind of fractionalization you see in F2 dynamics, for example. And here, this continuum is broad here, and is broad along this direction, but it's sharp along the other direction, because actually each individual, these are actually sharp excitations, it's just that they're superimposed on top of each other here. Okay, and so this is obviously a cartoon. What does it actually look like? So this is the real calculation. It was just taken from one of our papers, but the original paper was done by Yuan Wan and Peter Armitage in 2019, which I think, along with the 2017 experimental paper, kind of kickstarted a lot of the excitement and developments in looking at this nonlinear response to magnets. This is what it looks like in frequency. This is what it looks like in time. You can see that at when t equals tau, you get this, it's not so visible, but you get this kind of enhancement here. This is exactly because it's kind of echo, kind of like enhancement. And so you can see here that you have this blot along this direction, like this blotting, but very sharp along the other direction. And this is kind of, let's say, a general idea of why nonlinear response might be interesting for looking at continua. Because if you want to think about how can you tell these two situations apart, in this situation you have a very broad, so the pink is a very broad peak, but the broad peak is actually due to a lot of sharp peaks superimposed. Whereas here you just have a very, very broad peak, which is very broad. Okay. And so how do you tell them apart? And in this 1D frequency space, they look identical. I mean, here you'll see the pink envelope. But in the nonlinear response, you can separate this out into two frequency axes. And so now you can actually space out this signal. And so part of it gets spaced out along the anti-diagonal here. And so this is in chemistry usually called inhomogeneous broadening, broadening along this direction. And then the other part of it, so then if you cut along this anti-diagonal direction, you get this in chemistry called homogeneous broadening. So the kind of intrinsic lifetime or broadening of the individual excitations or emitters in chemistry. And that's exactly kind of what we see it reflected here. And Yuan and Peter kind of call this like a spit on an echo, this kind of sharp signal in those science.
So if I stare really closely at this plot and some of the data from earlier, there actually looks like there's some structure in the line.
In the line.
So there's like I can't tell if that's periodic like on blips or is that just numerical error.
You mean in this line?
Yes,
itself,
inside, right? Like it's kind of like bright, dark, bright, dark.
Oh, I think that's just because of the frequency resolution of the plot.
Oh, okay.
Yeah,
That's not real.
I just because it's on a diagonal, but the frequency, the plot is like plotted along. Okay. But the fact that it's a line is actually not super obvious because actually, if you look at the structure of the correlations or the correlation functions, the actual structure you expect is something like this. You actually expect a square like this. So you have these lines here and then another square here. Like I said, for this phase shifting reason, this signal disappears. And here actually, the transversalizing model is kind of special that these signals that are away from the main line here, they actually completely cancel out. So this cancellation is what brings you from this square-like feature to just a single line-like feature. So this, like, if you wrote out some of the individual correlation functions that make up this chi3, you actually see in some of them these squares, but some of them have squares with positive, matrix elements, and some of them squares with negative, and they just cancel away from each other. So that's how you get this kind of final thing.
Doesn't that mean if you do that there's some kind of correlation between the two? Whatever gives you positive, whatever gives you negative.
So
in any 2D spectroscopy, if you see these lines, that's usually right, Brian. What you call in chemistry coherences, high order coherences.
So what I mean is just that in the correlate, these expressions for these nonlinear susceptibilities, there's like different terms to do with the time ordering. Basically, if you look at in the individual terms, which you don't measure, you measure the sum of them. But if you look at them individually, some of them would contribute in the square, and the other ones would also contribute in the square. But those two would cancel away with each other. So the physical thing you would measure would actually just be the total thing that they cancel out. So I don't know if that's so there's no like actual like measure. There's nothing that you would measure that you would see this kind of in some sense.
No, but the fact that you have cancellation, does that really mean that you have to have some correlation in your material in that particular state?
No, you can just even in, let's say, simple
like metal.
It's kind of like the cancellations are more like you cancel away like disconnected parts.
Okay.
So like the super trivial example would be you just have a super trivial paramagnet where the spins all just aligned along the same direction.
Okay.
You can have a process in which you go from a spin pointing this direction. You go to the you flip the excited state and you go back to the ground state. You can have another process in which you start with spin this direction, you go to an excited state, and instead of going back to the ground state, somewhere else in the system, you excite the system and then go back to the ground state. these two processes basically contribute the same, but they cancel. They basically cancel away with each other. And so they're just, it's like a bookkeeping thing as opposed to a physical coherence thing.
Somehow this kind of bookkeeping is different from, say, like the normal Feynman diagram connected. components.
It's kind of similar, actually. I mean, you can kind of think about it as basically disconnected pieces canceling away. I mean, there is a kind of way in which it's oops, sorry, I didn't there is a way in which you can think of it as basically just the sequence in which you create an excitation and go back to that create an excitation somewhere else, and here you do it, and now you just basically do it somewhere else, and so these are uncorrelated with each other. And then these two things, here the energy of the state is just twice the energy of these because there's no interaction between them, and so then these things just cancel out basically because only the assumption that these two things are basically independent.
Right, there's some kind of there has to be only the connected component.
Exactly. Yes, exactly. Yeah. So the structure of these chi's is basically this nested commutative structure basically is what it means that all the disconnected parts cancel away. So you just left with the connected pieces. So this is it's the special structure kind of inbuilt into the correlation matrix, onto the chi's, I should say. Okay. So we were looking at the transfer Ising model, okay. And so we get this nice clean signal. Okay, so let's deform the transfer Ising model a little bit, okay. Make it a little bit more tricky. So what's the simplest deformation? You just add a longitudinal field. Okay. So now these domain walls they actually get confined together. Why is that? Because if you have a longitudinal field so along Z, if you have a big domain, you have a lot of spins misaligned with the field. That's very costly. Okay, so the system doesn't like these huge domains. So you actually split up this continuum into this sequence of barren states. And so you can think about it, it's like a mini kind of confinement scenario. So you sequence of barren states, and this basically lowest barren state you can kind of think of as like a single flip spin. The next one is going to have two flip spins, etc., etc. But you can also think of it as like barren states of increasing size. Okay, so what happens so this is what happens to the linear response when you add a lot onto a field. You just chop it up into this discrete sequence of barren states. So what happens here to our feature, a nice feature here, is you increase the confinement. You start seeing this additional thing up here. So this, is actually present here. It just cancels away because it's a continuous feature. So it reappears because of the discretization. Then you get some weird kind of stuff going on here, right? So I've gone all the way up here. Okay, so you get a kind of square grid-like structure emerging. So I can zoom in here, and I can also remove this phase twisting effect because I'm a theorist, and just plot this. Okay, so now we have a very weird sequence of colors that got complicated. But if you stare at it long enough, like a postdoc did, you can actually label every single process here and get extract all the energies. And I'll just break down one particular process for you, which is this. I've just zoomed in on this one here. There's this kind of blue continuous feature. So this is a sequence in which you break the domain of length 3 into two domains of length 1. Okay, so you think about starting at t equals 0 in the ground state. You activate this operator here to the left over here. You create a domain of size 3, so it's 3 flip spins. The second pulse acts over here. It creates two domains of size 1, so basically 2 flip spins. And now at the end, basically this operator I can act left or right. And I act it here left, and then it combines together again. So this is a sequence in which you basically break up, you think of it as breaking up a domain of size 3 into 2 of size 1. And the reason why, this, I drew this, why this only happens here and not here or here, is because the small, if you want to break a domain into two smaller pieces, you have to have a domain of at least a size 3. If you have only 2 flip spins, you can't break it into a smaller domain. So the minimum size is 3, right? And so then you can also do it. You can also break it 4 into 2 plus 1, 5 into 3 plus 1, etc. So these are these other kind of continuum. And then if you go to the next level, here at 4, you get break 4 into 1 plus 1, 5 into 2 plus 1, 6 into 2 plus 1. You go again at here, it's going to get fainter and fainter, but this feature here you can again break 5 into plus 1 plus 1, 6, etc. Right? So you have this kind of sequence of breaking kind of domain walls. So at the end of the day, you in the linear response, you have this just all the information you have is just a sequence of Banach states. But in the nonlinear response, you have an incredibly rich and complex spectrum. You should also remember that I've only cut out, I've only shown one chi3 and not the other chi3. I've only focused on the kind of lower quadrant of this chi3, and I've also not shown you chi2. I've also only shown the imaginary parts. So there's a lot of information here, right? And there's a very rich and complex spectrum. And it tells you not just about the excitations and their energies, but also how you can kind of decay from one to the other or go from one to the other. And there's a lot of related works on the transfer Ising model. Okay, so a lot of people are interested in this because it's the easiest model to look at. So as a theorist, this is the first model you're going to look at. The disadvantage here, well, not disadvantage, but one thing you might worry about is that this is a theoretical calculation. Now, if you do an experiment, you'll have this plus the other chi3 plus chi2 plus temperature broadening plus experimental resolution plus actual material parameters. So you may be wondering whether all of this gets washed out and there's actually nothing interesting you can learn in a real magnet because the interpretation will be too difficult. So obviously we were also worried about that. So we looked at a real magnet, a real Hamiltonian for a real magnet. We didn't look at a real magnet. we computed quantities for a real magnet. So we looked at a real Hamiltonian. So we took a cobalt niobate, which is quite a famous 1D spin chain compound. And it's been very well studied as Hamiltonian. It's been very well characterized in recent years. And it has like a transverse Ising model-like structure. So there's an Ising interaction here. There's a transverse field and a longitudinal field. And it's neutron scattering spectrum is known. These are from Matthew Kalea's group, Leonie Woodland. We're just looking at Q equals 0, remember, so we don't have all this rich Q information. We only look at Q equals 0. And you can see here the sequence of kind of Banach states, and that's kind of similar to here. And so if you look at the chi3, nonlinear response, there's a lot of actually different features. All the details in the paper, I'll just highlight one, which is what I was just talking about. That if you're at high temperature, so above the 3D ordering temperature of this material, so this longitudinal field is 0. This longitudinal field is induced by the 3D long range ordering, which induces some inner chain kind of like potentials. If you're at high temperatures, then you can basically, if I zoom in here, you can kind of see this feature I just spoke about. So this sharp feature here is due to this domain wall continuum. And it's broad along this direction, like we've seen in your response, but it's sharp along this direction, which tells you that's kind of this sharp fractalized continuum. And there's also other features. Then if you go down to low temperature, where this field, longitudinal field is activated, then it looks more like what I had, where you have this kind of smooth out response. Again, if you zoomed in close and you resolved everything, you could see this kind of complex information I had before, but realistic, it's possible to see that. So that's what you might see in a real magnet. And so we're interested in a lot of future directions along here. You think about more generally nonlinear dynamics of kind of confinement or mesons, string breaking. But people like to use the transfer Ising model for using these kinds of terms. There's a very famous transition in this material where you have this emergent E8 symmetry. So you can think about looking at the nonlinear response to that. And then we're also, looking at the permanent phase of this material. We have regular magnons. There's some interesting magnon decay going. What does that look like with nonlinear response? Okay, and then I have like maybe 2 minutes left, or 2 to 3 minutes left. So let me just, there's another, why. So this question about why. There's another super easy, and I think it's super easy. I can give you 2 slides. Explanation of when nonlinear response might be useful or interesting. And it's a very simple argument, so I can definitely cover it in a minute. So this is the case of hidden or dark excitations. So in linear response, you look at correlations like this. So then you look at matrix elements like this. Let's say you have a conserved magnetization in your magnet. So conserved MC, say. So and your ground state doesn't break this MC. Okay. So then your ground state has a particular conserved magnetization. S minus will change that magnetization by 1. So here the excitations that you access are these dipolar excitations. Okay. So your magnet has this huge energy spectrum, but in linear response you'll only see a subset of those excitations, those that obey this kind of dipolar selection rule. Now there are ways of getting around this in linear response. In RICS, if you treat RICS actually correctly, there's some intermediate process in the middle, and so this actually can give you it's not direct, but you can extract from this also information about non-dipolar like excitations. Some ESR experiments with this coupling between the magnetization and the electric fields. You can also activate these kinds of modes. And then of course the simplest thing is you just break this conserved magnetization, so you just break the symmetry. So if you just break E1, then you can obviously have hybridization between dipolar modes and other kinds of modes. But let's say that you have a magnet that has this conserved magnetization. Okay. If you look at the nonlinear turnover response, you look at matrix elements like this. And so now, these excitations in the middle here, they've delta m equals 2. So you can access quadrupolar excitations. So by going, if you have this kind of system, by very naturally going to the nonlinear response, you can measure kinds of excitations that are kind of invisible to you within the linear response. And there's I'll just tell you that there's a model in which, I won't give you the details. There's a model in which you can do this very easy Heisenberg model with single ion anisotropy. The grand state is all the spins point up or down. Okay. The excitations are, there's a 1 magnon excitation, where you go from +1 to 0. There's 2 magnon excitations, and then there's a special quadrupolar excitation, where you go from +1 all the way to -1. So this is a change of c by 2. This is activated by a spin operator, but this is activated by a quadrupolar operator. And in the linear response, if you look at that cut here, the single ion band state should be here, but in the linear response you won't see it because of this dipolar selection rule. So you'll only see the magnons. But in the nonlinear response, I won't go through this sequence, but in the nonlinear response you see additional peaks. And these additional peaks are exactly due to where you have this intermediate state of this quadrupolar excitation. So if you look at this, these are these single ion band state peaks or quadrupolar peaks. And if you compare this, for example, to a, so the other peaks, these are just the dipolar peaks. And you can compare the spin 1 model to like an analogous spin half model. Analogous in the sense that it has a similar grand state and similar physics. And you can see here the difference is that this has this additional peaks, and these additional peaks are due to the spin 1 quadrupolar excitations. Okay, and then just to say that even if you break this symmetry, so you no longer have a conserved magnetization, then in the linear response, it becomes visible again. So this is the linear response. You see 2 peaks now. Beforehand, this peak was invisible. Now it's hybridized, so you can see it again in this linear response experiment. And the intensity here basically tells you something about like the dipolar character. For dipolar character, I've defined as basically this weight. So here, this is a very small dipolar character. This is a very large dipolar character. And so now, does this have a small dipolar? So then you could ask, okay, are these dipolar excitations or quadrupolar excitations? Like maybe this excitation has a small dipolar character just because it's a very weak dipolar excitation. Or maybe it's a small dipolar character because it's actually basically a quadrupolar excitation and just a weak mixture of dipolar. So if you look at the nonlinear response, and that's a little bit more interpretational. Here there's an equal sign, here there's a wavy equal sign. But under this wavy equal sign conditions, and if you look at this line peaks here, these basically tell you about like the quadrupolar weight, and quadrupolar weight is defined basically as this here, okay, or the quadrupolar character. And you can see that this is very large, psi 1, because this is basically the single ion band state excitation. That's what it originally is, and it's very weak for the other one because it's basically dipolar excitation. So even in case in which you don't have this conserved magnetization, and this excitation is still visible to you in linear response, you can tell something extra about the character of the excitations by looking at the nonlinear response and looking at the intensity of certain peaks. Okay, so it's useful even with or without this, asymmetry, potentially. For the directions, see, I showed you just a ferromagnet here. We're currently looking actually at more complex magnets. I just presented here, and you can actually see the same thing in this iron iodide, which is a famous kind of triangle lattice spin 1 compound. You do the same calculation. You see a similar peak here, sequence of peaks. And again, it tells you about the quadrupolar nature. The non-frames doublets would be interesting, whether there is no dipolar character, purely quadrupolar, octopolar, and certain things like condensation and maybe even more exotic quadrupolar modes. Okay, well, I'm going to stop there and say that, going beyond linear response into nonlinear response, on the one hand, it poses a lot of challenges, conceptual challenges, in terms of thinking about the responses and the interpretation. Technical challenges, particularly for the experiments. You might notice that it didn't show you too many experimental results. That's because there aren't too many experimental results, because they're extremely challenging experiments. And most of them have been done for magnets by this group at MIT. But there's also a lot of opportunities, okay? So it's potentially a new perspective, a new window into quantum magnets and many body systems we're generally thinking about, not just the kinds of correlations we've been thinking about up until today, which typically these, two spin or single time correlation functions, but these more complex higher order correlations. It could maybe help identify the underlying nature of just continua, that's the hope at least. And I think it'll also help you access these multipolar excitations, also more complex band states in this cobalt niobate case. I didn't show it to you, but if you go to finite field, you can actually identify kind of quite complex band states that are, you can't see in the linear response. And so, I think nonlinear spectroscopy, I hope, going forward, will be a promising new method to get new insights on quantum magnets. So hopefully you'll hear more about it in the years to come. Thank you.
Yeah, so the other kind of, famous application of these ideas to the realm of liquids is what happens when your system is disordered, period.
Oh, yeah.
Right, and so, are the directions you're thinking about with regard to applying it to spin glasses or to random field spin models?
No, actually, I haven't thought about it at all. That's a great question. Yeah. Actually, no, I have not thought about that. Yeah. But yeah, that's a great, that's a great idea.
Yeah, I mean, the experimental challenge in the liquid context is you have a broad, linear first order response spectrum simply because the system's disordered, and you'd like to separate that out to see if you can actually learn dynamics.
Right. Okay, actually, I haven't thought about that at all, but that's absolutely, that's brilliant. I do actually think that, I mean, I guess for us at the moment, you might notice that I was basically just talking about transfer isomodel for cyclosis. So we're still kind of at the stage of looking at super simple models, and so I think that spin glasses, that's definitely, I think an interesting direction. But definitely a level of complexity is beyond what we're currently.
Well, I mean, in a sense, it depends what questions you ask, right? So if you're trying to get all that very, very detailed picture of, I have 3 spins and 2 spins, and you'll lose all that detail, but maybe you get other kinds of.
That's true. Yeah. We'll call it exactly. Yeah, no, that's a great question. Yeah, I haven't really thought about that at all, but that's absolutely excellent. Yeah, and I think that I only super briefly showed you that there's I had mentioned this the word last came up in one context of my talk because I had mentioned these experiments by Peter Armitage where he had looked at this marginal Fermi glass. But really, this is just like so it's a disordered semiconductor, the doping disordered semiconductor slide. But basically, in terms of modeling, it's basically just like a collection of 2-level systems. I mean, each doping you can think of like so it's like a random collection ensemble of 2-level systems. And so it is kind of like that's very, I think, closer to the last kind of thing exactly. And so there they do have some nice work on looking at nonlinear response for this kind of
So thanks for the talk. So a question about the computation. So for linear response, I would normally switch to massive errors, but now you have these nested correlators. So how would you actually compute these?
Yeah, so I didn't talk at all about how I did any of the calculations that I showed you. So most of the calculations that I showed in this talk are real-time exact diagonalization. So either in this final quadrupolar case I mentioned to you, this conserved magnetization actually means that the ground stays in all this spin-up sector, and because of the conserved magnetization, you only have to consider the sector with 1 or 2 such spins. So the Hilbert space is actually quite small. It's not exponential, but it's like quadratic in the system. So we can do like 100, 200 spins easily with full exact magnetization, and we just do real-time evolution. So we just time evolve the ground state, and then do the subtraction procedure that I mentioned. In the this transfer to the isomodel stuff I mentioned, the excitations use the natural excitations use domain walls. So you can just truncate the Hamiltonian into the space of 2 and 4 domain wall states, and just forget about the higher domain wall states. And again, just do exact diagonalization and real-time evolution. And then other things we've looked at, like we have some classical dynamics as well, and there again it's just real-time evolution, classical dynamics. And we're also doing some nonlinear spin wave theory calculations, and in those cases actually doing directly in frequency space. So we basically, so far, only ever do either real-time evolution, or we directly in frequency space. So we avoid having to do that.
So analytics is not really possible then?
Sorry?
So it's not really possible to do analytics in this case? Or?
I mean, it can be possible. I mean, there's some papers where where they've done like basic Keldysh, so you have to do Keldysh essentially. So there's some work on the transfer model, for example, by Rahul Nandikshoor at Boulder, but there's some complicated not this one, this one. And it's some complicated Keldysh,
So real time anyway. So you have to work in real time.
Yeah, they do it anyway in Keldysh. Yeah.
I'm kind of, so looking at this spectra, it's so complicated. I'm kind of curious about like how in practice, if you were to do an experiment, you would actually interpret it. Because in some sense, the nice thing about linear response is you don't have to do anything after you measure it. Like when you look at neutron scattering data, because of the energy ordering that you talked about, you can basically just identify what's going on, and you have some well-defined selection rules.
Right.
And then of course we can fit a model to it and get other parameters, but the value in the data comes before you even fit the model. But here, how can I identify specific features as specific things without like already knowing exactly what the Hamiltonian of my system is?
Yeah, I mean, I think that's the kind. Yeah, I mean, that's a great question. I think that's the kind of what we're still working through because it's such a new,
you showed all of these different features, and they're clearly
right.
features. But if I just looked at it, I have no idea what's going on. Like I don't know what.
Yeah. But I think this. I mean, if I looked at this, I also wouldn't. It's just a sequence of peaks. I also wouldn't know.
I guess so.
What's going on, right? And I mean, so yeah, you're right. I mean, there's definitely more complex information, and it's also less intuitive. You're as an expert, you're completely used to looking at.
That's true. And then I also have
certain factors, and so I could ask you, I could tell you, I have a particular crystal, I have a particular magnetic order. You qualitatively predict for me basically what the neutron scattering response looks like. Without knowing any of the details. For the nonlinear responses, the first calculation of transfer Isaac model was done in 2019. So I mean, I would say that we're not at all used to it.
But so when your postdoc was staring at this for just a bit of context, were they just like looking for two bright spots and then looking at the energy difference and then trying to figure out what possible excitations would have those energy differences? What were they actually looking at when they were seeing?
Yeah, I mean, so obviously we had the linear response energies, and so you can kind of like already kind of
and then just match it, right?
Yeah, I mean, it's a little bit of matching. There's also a little bit of physics. There is. I think it's not even in the backup slide, is it? There is. I briefly mentioned these double-sided Feynman diagrams, which are basically a way of. Are you familiar with these? Or?
No.
Okay. So they're basically a way of organizing the different processes that can contribute.
Okay.
So we heavily actually, use this kind of bookkeeping kind of thing.
Yeah. So you have an idea in your head of the different processes that can
yes,
occur.
exactly, and the ways in which those processes can occur, the energies that they can occur at.
Yeah.
I mean, one of the things, in these Chi3s, you actually can, if you know the linear response energies.
Yeah.
Right. You can just plug in. These energies, all these energies here, right? If you know all the linear response energies, let's say you don't care about the measures elements, you just want to know what energies are possible, what peaks are possible. You just take all the linear response energies, just plug them in here. You get a crazy sequence of like features. Now you're not guaranteed all of them will appear because some of them might have zero matrix elements.
Yeah.
But at least know what is possible, right? You won't have more than those features because that exhausts every possibility, right? So you might have less than them because of cancellations, but you can already basically just put in based on linear response what kind of structure I might get.
Yeah.
And it's a question of cancellations of these kinds of things, and let's assume that you know the linear response structure.
To inspire your postdocs to do this, you tell them the story. That's exactly what Heisenberg did, and look what it led to.
Yes, they're staring at
that's what he did for the spectral line, and then it took 5 years to figure out those eigenstates of the
But at this point, a computer is actually probably pretty good at identifying all of those differences, and then if you can list out all the possibilities, you can probably just automate.
Right. And so I think the real. I mean, I think difficulty is not in let's say not the locations, but in extracting the information, right?
Yeah.
I mean, in particular, I typically, mentioned here, for example, where there's like fractional, due to fractionalization, these kind of things. I've also not really focused on too much here, like Magon decay and broadening, because one of the ways in which actually, again, like these Fermi glass or these superconductors, one of the ways actually what people are interested in is really that because it's in this 2D frequency space, by looking at different cuts, for example, for a simple two-level system, basically different cuts, one will give you like a T1 time and one will give you a T2 time, as you can like independently get those out. So that's actually what they measure in this marginal Fermi glass kind of thing. So that, you can potentially get more information, one way of thinking about it is that if you have a particular excitation, your linear response just gives you a single viewpoint perspective or vantage point on it. But with nonlinear response, you can maybe kind of look a little bit, around it a little bit more and get a little bit, new perspectives and maybe new information. And so maybe you can disentangle if you have two modes that are, superimposed. And so you basically can't disentangle them in linear response. by putting in the 2D frequency space, you might be able to disentangle them. You know, decay, different kinds of decay. So decay that's due to interactions versus decay that's maybe due to disorder. You might also be able to separate out into along different.
One of your examples that you showed here actually is a good example of that. Maybe it was the marginal Fermi.
Oh yeah.
And you actually can see if you look along the diagonal. In some cases, you have a very round shape, versus you have a very elongated shape, and that's interpretable right away in terms of the amount.
But so
so there's T1 versus T2. Exactly. Exactly.
Or maybe
right.
an example like in a magnet like ruthenium trichloride, but it doesn't have to be. It can be any spin half magnet that's maybe a quantum spin liquid, but has some terms in the Hamiltonian that if it was an ordered magnet, allows for continuum from a magnon decay.
Right.
But if it's a quantum spin liquid, you also get a continuum.
Right.
You get continuum for the same reason because you have multi-particle states, but they're different multi-particle states.
Yeah.
Could you distinguish those two scenarios? Forgetting about that, it's actually magnetically ordered.
I mean, I think it might be tricky. You know, this work that we did with Youngbeck actually was, inspired very much by, I guess, work with the three collaborators on these pyrotor materials. So we did classical linear Lifshitz on the Guittard honeycomb model.
Yeah.
And so for the linear response, it's already known there that you can basically reproduce qualitatively the linear response of the quantum model with the classical dynamics.
Yeah.
And you have this nice paper about it on the pyrotor.
Yeah. But that's that's continuum because you don't have blocks, you don't have
Right. So in the Guittard case, it's because, in one case you have the quantum spin liquid and you have the classical spin liquid.
Yeah.
And they basically have a very similar, kind of response. So now you can say that the nonlinear response looks similar.
Yeah.
So in the quantum spin liquid case, you have these sharp lines, like in the transferability model, because you have this fractionalized continuum. If you use classical linear Lifshitz for this classical spin liquid, you also actually get these kind of sharp lines. So originally, I think maybe the hope was that these kind of sharp lines, the fact that you have this inharmony blowing on one direction and sharpness on the other direction, might be able to tell you that, okay, this continuum is a fractionalized continuum as opposed to like a disorder continuum, where you go along both directions. But one of the tricky things is that it's another scenario where classical dynamics, it seems like, can give you a similar feature. So then again, classical dynamics for a pretty complicated state. But that's another tricky thing. I will say that in that case, the one good thing is that for a I'll just flash this as and finished my thought. For the linear response, these three scenarios all look very similar. This is a quantum spin liquid, a classical spin liquid, and a large unison magnetic order. So they all look very similar. In the nonlinear third order response, these two look kind of similar. I mean, here they're plotted quite differently, it's a large tell. But here there's like a sharp line-like feature. Here there's also a sharp line-like feature. These look quite similar. But these two scenarios, which in the linear response look almost identical, and the nonlinear response look incredibly different. So at least this distinguish between these two scenarios, you could maybe use nonlinear response. So if it's a continuum that's due to like this large unison magnetic order finite temperature, versus a continuum from like this classical spin liquid, at least those have different nonlinear response features, despite having similar linear response features. That's not a complete answer to your question, but I think that definitely that's something that people would like to work out, a more complete answer to your question.
Yeah, okay. Because originally, I think I remember when people like Youngbeck were originally writing out this, it seemed like we could just tell you if you have a spin-on continuum or if you have a magnon, but it's not so. I
mean, I think that's the hope, but I think like everything, it's never quite as straightforward as it first seems. And so it may be that the final answer is yes.
Right.
But I think it still takes. One has to be careful about checking everything and working and. So the answer to the question may be yes.